Let's consider a simple harmonic oscillator, and this simple harmonic oscillator is oscillating up and down, and because of that, let's say there is some air present, so it will be pumping air up and down, and because of that we'll see that it will produce something like this. Which means it will produce pressure which may look something like this. So here pressure is low, and then pressure becomes high, and then pressure is again low, and then pressure is high, and this all depends because the velocity of this guy is changing sinusoidally. So this guy, which is moving in the y-axis direction, has a velocity something like this. This is the velocity with respect to time, and that is why it is producing a pressure wave which is moving downward. So this is a wave, it's a pressure wave because the pressure is changing, and it's not that only this portion will always stay at high pressure. After a while what will happen, this may become a low pressure region and the other guy may become a high pressure region, all because this guy is moving up and down. So this simple harmonic motion, which was sort of restricted to moving the mass up and down, has now translated to a wave motion, a pressure wave motion. So this is a wave. Now let's see what happens if you increase the angular frequency or the frequency of this guy. What happens? Let's say this is the original wave. This is the original wave. If you increase the, if you replace this system by a system which has a higher angular frequency, you will expect a different kind of wave. Well, this is not a very good looking diagram, so let's try to make it look better. This is a sine wave. Okay, these are both sine waves. I'm sorry, they do not look like sine wave, but assume they are sine waves. What is the difference? The difference is that if you increase the frequency of the wave produced also increases. So the wave is determined by the frequency. That is one of the parameters that is required to explain a wave. What else? Let's say if we increase the amplitude of the motion, this guy goes really high up and really high down, then this will increase the amplitude. So this is what I mean by increasing the amplitude. So here it was, amplitude was, let's say, A1, and here the amplitude is A2, then A2 is greater than A1. So that is one more parameter that distinguishes two different waves. So these two waves differ in frequency and these two waves differ in amplitude. What else? Well, there's one more thing. All the time we are starting the wave at 0, which may not be true. You may start recording the wave, let's say from here or here or here. So a wave, you can start recording a wave from 0, from the situation when time equals 0, amplitude is also 0. So this is t and this is amplitude, this is 0, but you can also record the wave when there's something else. Okay, so this is the third parameter which is needed to describe how wave is behaving, and all of this can be combined to be written as y equals A sine omega t plus phi. And this is nothing but the equation what a simple harmonic motion satisfies. So y is the amplitude which is changing in time, a is the amplitude, so this is the amplitude at a certain time, and a is the maximum amplitude. Omega is the angular frequency, where we know that omega is also written as 2 pi f, and where f is the frequency, and by frequency we mean number of cycles every second. And phi is a parameter that tells where does the wave start. But this is simple harmonic motion. So what is there should be some difference between the two things, between simple harmonic motion and waves. What is that difference? We are writing the same equation for both of them. The difference is that the simple harmonic motion is localized in one certain place. So this guy is not really moving at all in one certain direction. It's moving up and down, but it's not really moving in one certain direction. But this wave is going down, is moving downwards, and it has a velocity v. So it has a velocity v, and so it has a velocity v, and that is why it is also traveling in time as well as distance. So waves travel in time and waves travel in distance also. I think I meant to say pressure here. That is what I meant to say when I was describing how the pressure was changing. Okay, what do we mean by travel in time? Travel in time means that same as simple harmonic motion, that the amplitude changes as you travel forward in time. But you do not really have to draw just time on the x-axis. You can also say, you can redraw the same wave. It's the same wave, but also traveling in distance, which means x is also changing, and as x changes, amplitude changes. What is the relation between these two? The relation between these two is x equals vt. That any distance traveled equals velocity of the wave multiplied by the time traveled. Okay, so a simple harmonic motion has an amplitude that changes with time, and a wave has an amplitude that changes with time as well as distance, where time and distance are related by this formula. Okay, so this is waves, and the only three parameters are these. Okay, you can also talk about few more things. Let's talk about few more things. So we said in one of the previous lectures that time taken to complete one cycle is a time period. So t is the time period, and we are also saying that it's traveling some distance in that time period. So in time period it travels some distance, and this distance is called lambda, or the wavelength, where again we can say that lambda is nothing but vt, where v is the velocity of the wave. So we are just sort of expressing the same change in amplitude using two different variables. Again, these two variables are simply related by this formula. So they are not sort of independent of each other. They depend. They are independent. They are sort of x is nothing but a multiplication of t. But there are two views of seeing them, because t is a change in time and x is a change in distance. Okay. Two more things. First of all, we saw that pressure wave, and we saw that pressure waves which was behaving something like this. Not a very good drawing, but let me try. So the pressure wave was moving in this direction, and the amplitude was also changing in the same direction. You see, the amplitude is higher here, and the amplitude is lower here. Why? Because pressure is lower. What is the amplitude we are talking about? In this case, the amplitude is, there should be something that should be amplitude. What is that is changing? It's the pressure. So it's the pressure that is changing with distance as well as time. So in this case, the pressure wave that is traveling, not just motion, not just y. Y can have any meaning actually. Y, when we say amplitude, it can have any meaning. So in this case, it's the pressure that is changing. Okay, so these kind of waves in which amplitude and the wave velocity are in the same direction. You see, pressure is changing in the direction of the motion. Pressure is changing in the direction of motion. And this kind of waves are called longitudinal waves. You can have a different example. Let's say if you have a simple harmonic oscillator that is going up and down like this, simple, let's say a vibrating filament, and it's connected with a rope, and you let this thing go up and down, you will see that rope goes up and down like this, because there's a wave that starts traveling through the wave, through the rope. Now in this case, the velocity of the wave is in this direction, but here by amplitude we mean up the normal position, how much the rope is above the normal position, and this is the amplitude. Okay, but there's a difference from the previous case. In this case, we see motion is in this direction, but the change in amplitude is in the perpendicular direction now. So these kind of waves are actually called transverse wave. These are transverse waves. And you can have other examples like ripples on water is a transverse wave. Okay, so we will talk more in following lectures.